lesson is about the behavior of conductors in electric fields, and we'll see this is applicable when we talk about electric circuits. So things that we'll learn today are how in equilibrium the electric field inside of a conductor is zero, how in fact the surface of the conductor is an equipotential surface, and we'll see there's also a correlation between the curvature of the surface and the strength of the electric field. So looking at conductors, we know that they have free-moving charges. So if there is an electric field inside the conductor, the charges will respond to that electric field. And this gives them some interesting properties to the conductors. For example, we already know that any excess charge in a conductor will be gathered on the surface, and there'll be no excess charge in the interior of the conductor. So property number one, in an electrostatic equilibrium, the electric field inside of a conductor is zero. So in equilibrium, the charges will not move. And if the charges are not moving, that means there's no net electric force on them, which means that the electric field is zero. And this is the reason for which the electric field inside of a conductor is zero. And we can see here, plotting the electric field as a function of radius. The electric field is zero out to the radius of the sphere. This is a conducting sphere that's positively charged, and then drops off as 1 over r squared from the surface of the sphere to infinity. So the electric field jumps at the surface of the sphere and is equal to kq over r squared. Now, and if we were to actually exert a force on the electrons inside, then the electrons will start moving, so then that will go against our assumption of electrostatic equilibrium. So again, in electrostatic equilibrium, there's no net force inside the conductor, which means the electric field is zero. Now, if the external force changes, then the electrons will start moving until they counteract the force. And we can see an example of this if we were to place, so we have here our example of the charged conductor, which creates an electric field outside of it, even though inside the electric field is zero. And then we put a neutral conductor in the electric field of the charged conductor. So this neutral conductor will stay overall neutral, but the charges will reassemble in response to the electric field of the charged conductor. And they will reassemble until they counteract that electric field exactly. So then inside the neutral conductor, the electric field again will become zero in electrostatic equilibrium. Again, if the electric field inside were not zero, then these charges will keep moving until it becomes zero. So even if you put a conductor in the electric field of another object, inside the conductor the electric field actually stays zero as long as we have equilibrium. Now, if the electric field inside is zero, because the electric field is the gradient of the electric potential, that means that the electric potential inside the conductor must be constant, which is what this part of the sketch now indicates. If we're plotting the electric potential, it is constant out to the radius of the conductor and then drops off as 1 over r outside of the conductor. Another property of conductors is that the electric field at their surface is perpendicular to the surface. If the electric field had a component that was not exactly perpendicular to the surface, but had a component along the surface, then the charges in the conductor will move until this net electric field along the surface disappears. So as a result, the electric field of a conductor is always perpendicular to its surface. So in equilibrium, the electric field is perpendicular to the surface, but now we know that what is perpendicular to the electric field are these lines of constant potential, the equipotentials. So as a result, the surface of a conductor is at a constant potential, so it is an equipotential. Another property of conductors is we can determine the strength of the electric field based on the surface charge density. So the strength of the electric field going away from the surface of the conductor is directly proportional to 4 pi k times the surface charge density of the conductor. And the electric field will point either directly outwards if the conductor is positively charged, or directly inwards at the surface if the conductor is negatively charged. And finally, another property is that the strength of the electric field at the surface of the conductor is related to the curvature of the surface, in the sense that if the curvature is smaller, the field is stronger. And if the curvature is greater, as in point P here, the field is weaker. So the field at point P prime is stronger than the field at point P. And we had an indication of this already in an earlier plot that I used, which shows a greater charge density here near the narrower curvature than around the broader part of this object. And there'll be a separate demonstration video linked off to the lesson site that actually shows this as a true fact by measurements done in a lab. So to summarize the properties of conductors, the electric field inside of them is 0. The electric potential inside of them is 0. All of the charge, if there's any charge on the conductor, is distributed on the surface. The field of the surface is always perpendicular to the surface of the conductor, and as a result, the surface itself is an equipotential surface. The magnitude of the field is directly proportional to the charge density, and it's also related to the curvature, with the field getting stronger when the curvature becomes smaller. So let's consider a simple example now. We have a charged solid metal sphere, so a conducting sphere. We have the radius and we have the electric field at the surface, 3,800 newtons per coulomb, and we are told it's actually pointed toward the center of the sphere. So if the electric field is pointing inwards, then the charge on the surface must be negative. So this is a negatively charged conducting sphere. The question is, what is the potential at the center of the sphere? So taking a look at our problem, we are given the radius of the sphere, and now at the center, if a total charge in the sphere is q, at the center, all that charge being distributed at the surface of the sphere is going to be exactly a distance of r away. So then at the center, the potential is going to be kq, the total charge on the sphere, over r, the radius of the sphere. We're not told, however, what q is, but we can determine that from the strength of the electric field. We know the expression for the electric field is kq over r squared times r hat. So then q is going to be the product of E and r squared over k. And q is negative because we're told that the electric field is pointing inward to the surface. So then we can substitute this expression for q in here to determine what the potential is. And that ends up being minus 760 volts at the center. And so I've obtained volts from newtons times meters divided by coulomb, realizing that Newton meter is a joule, and a joule per coulomb is a volt. So again, as I've mentioned before, dimensional analysis is important in verifying that a problem is correctly solved. So let's take a look at what the graph of the potential and the electric field strength look like for this sphere. So here's the potential, here's the electric field strength. The potential is constant out to the radius at minus 760 volts, and then drops off as 1 over r outside. The electric field is 0 out to the radius, jumps at the radius to the value that we're given, and then drops off as 1 over r squared. And both are negative because the charge on the sphere is negative. And finally, there's 2 more examples in these slides about calculating electric potential that you'll find solved in separate problem-solving videos.